Imagine a box in front of you. Within the box is a bomb, which has a 50% chance of detonating. Now, if you were to place a cat inside the box and close the lid, what would be the outcome when the lid is reopened? What we have here is the Schrodinger's cat theory, proposed by Austrian physicist Erwin Schrödinger. According to the theory, before the lid is opened, the cat is both dead and alive. Until the lid is opened and the results observed, the state of the cat is just a blur of possibilities. When Schrödinger proposed this theory, he wanted to show just how absurd quantum physics is and how it didn't make any sense. The theory proceeded to become one of the greatest misconceptions in modern physics history, but it also ended up setting up a foundation for newer ideas. The misconception was that the state of the cat would only be determined if an observer was present. It was later proven that, even without an observer, a final state could still be determined. Quantum physics exists in a realm outside of classical physics, and has rules beyond common comprehension. At first glance, the theory of quantum physics makes no sense at all. Even Albert Einstein questioned the concept of quantum physics. He believed that God does not play dice, as many core theories of quantum physics rely heavily on probability. He theorized many experiments and trials in an attempt to prove that quantum physics was false and tried to explain how things function without using quantum theory. After his death, it was proven that quantum physics did exist, and many things, such as complex molecules, magnets, and even solid objects, would not function without it. When we're dealing with very small things on the atomic level, conventional physics starts to break down. And when we're dealing with these small particles such as atoms, quantum mechanics comes into play. Quantum entanglement is a very interesting part of quantum physics. It occurs when a pair or group of particles fulfill certain conditions when they're generated, such as interaction with or in close proximity of each other. It is also a basis of a quantum computer. Consider two quantum entangled objects, A and B, where object A is here on Earth and object B is on the moon. If we were to measure the same property of both objects, object B on the moon must have the opposite result from object A down on Earth. Thus, no matter how far away it is, if we know the result of measuring A, we can determine the result of measuring B. In quantum physics, this measurement is done on a property known as spin. Every matter in existence is proven to have spin. Spin refers to a value called the spin quantum number of a particle, which is the amount of intrinsic angular momentum a given kind of particle has. This number is always a value in the form of n divided by 2, where n is a positive integer or 0. Let us imagine two spinning objects. To measure the direction of the spin, we must define an angle to measure. If the object is spinning towards that angle, it will be an upward spin, while if it's spinning in the opposite direction, it will be a downward spin. We can only measure spin towards a single angle, so when the object is spinning neither towards or opposite of said angle, we calculate the probability of whether it will be an upward spin or a downward spin. The probability changes relative to the object's spinning angle. The closer it is to an upward spin, the higher the chances it would be one. So if we have two quantum entangled objects, and the measured spin of the object is upwards, then object B measured in the same manner would be downwards, the opposite. It is fascinating to see that these two objects can communicate beyond the speed of light, to be able to share information across far distances. The theories of quantum mechanics prove to be very challenging in the philosophical world. The Everett interpretation and the uncertainty principle are two explanations for the states of superposition in quantum mechanics, in which an object can be in many places at the same time, and the result of an experiment can be both A and B until it is measured. The Everett interpretation, named after physicist Hugh Everett, is a branch of the many worlds interpretation, which suggests that all outcomes of quantum measurement exist, just not in the same universe. The wave function collapse is when all possible results of a function reduce to a single observed result. The every interpretation denies this phenomenon and instead explains it as a branch in reality. The many worlds interpretation suggests that under certain conditions, the universe will branch into two paths. No one knows when the branching started, nor what conditions are required for the branching to occur. This is one of the theories which emerged from the Schrodinger's cat theory. It describes the alive and dead cats as being in different branches of the universe, with the both of them being equally real. The Everest system completely eliminates probabilities from existence and has a completely deterministic view. The uncertainty principle states that there is an inherent uncertainty when measuring the variable of a particle. When considering the momentum and the position of a particle, the principle states that the more precisely you know the position, the more uncertain the momentum, and vice versa. As an analogy to this theory, imagine you are blindfolded and in front of you is a marble. To determine the position of the marble, you must reach out and touch it. But by touching it, its position has now shifted and the velocity has changed. So in the end, we aren't able to measure both the momentum and the position of a particle due to the fact that while measuring it, the position and momentum would be constantly changing. The rules of quantum physics are often confusing and seem unrealistic, but without these rules, many parts of our universe would cease to exist. Isn't it fascinating how one object can be in many places at the same time, and how every result of a solution can have its own universe?